Today, we're diving into something we're in every single second of our lives, but we hardly ever stop to think about it: the atmosphere. It's this invisible engine, this life support system for the entire planet. And we're about to pop the hood and see how it really works. Go on, just try it. Take a really deep breath. Feels pretty simple, right? But what are you actually pulling into your lungs? It's way more than just oxygen. The air all around us is this complex, invisible recipe that controls everything from the weather tomorrow to the climate for the next 1,000 years. And that's the big idea here. The atmosphere isn't just there. It's not some passive bubble of air. It's a powerful, dynamic engine. It's constantly moving heat around the globe, shielding us from nasty radiation from space, and creating the very conditions that make life here possible. So let's break down how this incredible engine runs. All right, so first things first, let's look at the ingredients. What is this air we're all breathing actually made of? I'm gonna bet the answer is not what you think. So you'd think it's mostly oxygen, right? I mean, that's what we need to live. But look at this. It's only about 21%. The vast majority, a whopping 78%, is nitrogen. After that, you've got these tiny little slices for argon and a mix of other gases, including things like carbon dioxide. 78%. Just let that sink in. Most of the air you just breathed in was nitrogen, a gas your body doesn't even use for breathing. It's kind of a wild reminder that the most common things around us aren't always the ones we notice. And the part that's absolutely crucial for us, the oxygen that powers every single cell in our bodies, just 21%. It's this incredibly precise, delicate balance that has allowed all complex life on Earth to exist in the first place. Okay, so we've got the ingredients down. Now let's talk about one of the atmosphere's biggest jobs, being the planet's thermostat. Why is it freezing cold in one place and scorching hot in another? Well, it pretty much boils down to two simple rules. I mean, think about it. The sun is basically a giant furnace, and it shines on the whole Earth pretty consistently. So why isn't every place the same temperature? The answer is all about how that sunlight actually hits us. And here are those two big rules: latitude and altitude. First up, latitude. Because the Earth is a sphere, the sun's rays hit the equator dead on, like a spotlight. All that heat is super concentrated. But as you move towards the north or south poles, those same rays get spread out over a much bigger area, so the heat is less intense. Then you've got altitude. The higher up you go, the colder it gets. Why? Because the air gets thinner, it's less dense, and that thinner air just can't hold on to heat as well. It's the exact same reason why people go to hill stations in the summer to cool off. And you know what? We can see these principles in action on a much smaller scale. Have you ever noticed how big cities always seem to feel hotter than the countryside around them, especially on a summer night? Well, there's a name for that. It's called the urban heat island effect. All that concrete, asphalt, and steel in a city spends the entire day just soaking up the sun's heat like a sponge. Then, at night, while the surrounding fields and forests are cooling down, the city starts releasing all that stored heat back into the air. Add to that the fact that you have way fewer trees for shade, and you've got the perfect recipe for a hot spot. Okay, so let's zoom back out. From the city back to the entire planet. That same heat-trapping principle works on a global scale. We call it the greenhouse effect. And the best way to think about it is like the Earth's very own climate blanket. Here's how it works. It's pretty simple. Step 1, sunlight comes through the atmosphere and warms up the ground. Step 2, the Earth tries to cool itself off by radiating that heat back out towards space. Step 3 is the key. Certain gases in the atmosphere, greenhouse gases, trap some of that outgoing heat. They stop it from escaping. And that's a good thing. Without this natural blanket, Earth would be a frozen ice ball. So, what happens when that blanket gets too thick? Well, that's what we call global warming. When human activities, mostly burning fossil fuels, release more of those heat-trapping gases, we're basically making the blanket thicker. More heat gets trapped, the natural system gets amplified, and that leads to a long-term rise in the planet's average temperature. All right, for a final point, let's look at a totally dramatic example of how physical geography and the atmosphere work together to create the climate for an entire continent. We're talking about the Himalayas. It's a crazy thought, I know, but just imagine it for a second. What would happen to the climate of India if that massive mountain range just wasn't there? The impact would be absolutely staggering.
You see, the Himalayas act like a giant wall. They block the freezing, bitter cold winds that sweep down from the north. Without them, those winds would just pour into North India. You'd see snowfall, and winter temperatures would drop way below freezing. Not only that, the mountains are a huge part of what drives the monsoon system, so rainfall across the entire country would be completely different. It's a perfect, powerful example of how one single geographic feature can define the climate for hundreds of millions of people.
And that leaves us with a final thought. From the exact recipe of gases we breathe, to the way heat is managed across the globe, to the powerful influence of giant mountains, the atmosphere is an incredibly complex and interconnected engine. Every single part is in a really delicate balance. So the question we're left with is, what happens when we continue to change the key parts of this invisible, life-giving system? Thanks for watching.